Well, we are familiar with atmospheric pressure. Weathermen are always going on and on about atmospheric pressure, right? They're talking about the high pressure system and the low pressure system, and the barometric pressure is rising or falling. But the variation in the pressure of our atmosphere creates wind. Do you ever wonder, why is there wind? We know what wind is. It's air moving, right? But why is it moving? It has to do with changes in pressure. High pressure is generally associated with clear weather, and low pressure is usually associated with unstable pressure. And so we have regions of high pressure and low pressure, and they cause air to move, and it gives rise to our weather. Another aspect of atmospheric pressure is that as you go higher and higher in altitude, the number of gas particles in a given volume decreases. And so atmospheric pressure decreases with increasing altitude. As you go up into the mountains, we often say that the air is thinner, right? And you get out of breath more easily. You're not getting as much oxygen in from the air because there's not as much air. And the pressure of the air is less as well. There's just fewer particles. Pressure and density are related for gases. The pressure exerted by a gas depends on the number of particles in a given volume. Fewer gas particles mean lower force per unit area and lower pressure. If we look at these two jars and think about these little gas molecules, and they're zinging around, they're running into each other, and they're bumping into the walls. There are fewer particles here. We're going to have lower pressure. Pressure is the force divided by the area. The area of these two jars is the same. Each of these particles is going to hit with the same force, but in this jar there's going to be fewer collisions than in this jar. And so the overall force will be less and the pressure will be less. What is density? Mass divided by volume. Which of these containers has a larger mass of gas? The one on the right. They have the same volume. So this gas is more dense because it has more particles, therefore more mass in the same volume. Gas pressure is to blame for pain in your ears. When you fly, there's a change in pressure. They compensate with the pressurized cabin, but it still changes. It's not the same as it is on the ground. And so as you go up, your ears pop, and then your ears pop as you come back down. Same thing happens, you drive up to Kings Canyon, your ears pop on the way up, and then they pop on the way down. Mine often don't pop enough on the way down, and so then, like hours later, I'm still like waiting for my ears to pop. I hate that. What can happen, though, if we look at what's going on in your ear, you have an eardrum, and on the outside, your ear is open to atmospheric pressure, and on the inside, it goes through your eustachian tube into the back of your throat. What are they showing us here? Reduced external pressure. So you go up to the mountains, and the outside pressure now is lower. If your ear doesn't pop, you have more pressure on the inside, and that causes your eardrum to bulge out. And that doesn't feel good. If you don't have an ear infection, it's just maybe mildly uncomfortable. If you have an ear infection, that is really, really painful. And so that popping sound that you hear is when your eustachian tube finally has enough pressure on it that the pressure escapes and your eardrum can straighten out again. When you come down the mountain, the opposite happens. Now you've got pressure on the outside causing your eardrum to bulge in. And it seems to be harder, at least for some people like me, for the air to come back in than it is to go back out.
Where does it escape to?
Just into the back of your throat, not through your mouth.
Oh.
Yeah. When you're congested, everything's kind of a little bit swollen, and then your eustachian tubes don't open up as well. Babies have really tiny eustachian tubes, and so that's why babies often scream on airplanes. It's because their ears are killing them, right? Because they're just their ears aren't popping like they need to. Any other questions? Barometer. This is an illustration of a mercury barometer. So I don't know about you, but my kids like to play with water. And when they're in the bathtub, they just do all kinds of crazy things. They end up flooding everywhere. But they play with water, and I remember playing with water too. And I remember you could take a cup and you fill it up with water under the surface of the bathtub, and you turn the cup upside down and you lift it up, but you keep the rim of the cup under the water. Let's draw a picture. Blue's good. Okay, so here's the surface of the water. And you bring the cup up so that the edge of the cup, the opening of the cup, is still under the water. And all the water stays in the cup. And it's like, wow, look at that, because it's defying gravity, right? It wouldn't do that if it wasn't underwater. When you pull it up a little further, all the water rushes out. Did you ever wonder, why does the water stay in the cup? It can't come out because there's no way for air to get in up here. If there was a hole in the cup, it would come out. But what's pushing it up? It's the atmospheric pressure. The atmosphere is pressing down on the water, which supports the water in the cup. It's really kind of a crazy idea. A barometer uses mercury. Mercury is really cool stuff. It's a liquid at room temperature, but it's a metal, and it's really heavy. Its density is about 13.6 grams per cubic centimeter. And so it's really dense. It's almost 14 times as dense as water. And there was a guy named Torricelli, and he was the one who's credited with inventing the mercury barometer. So he took a long tube, like a giant test tube, he filled it with mercury, liquid mercury, and he inverted it into a dish of mercury. And we're like, well, how do you think of doing that? Well, maybe he had been playing with cups in the bathtub. And here's liquid mercury, and hey, I wonder if it would do it with this too. Well, what happens is some of the mercury will stay. You can get up to 760 millimeters of mercury to stay. That's a distance. So 76 centimeters. But above that, doesn't matter how long your tube is, there'll be a vacuum up there. So part of the mercury comes out. Water doesn't do that just in a cup, right? For water, you'd have to have a tube that's about 32 feet tall to see that it doesn't stay all the way to the top, because water's not nearly as dense. But what's happening is atmospheric pressure is pressing down on the mercury, and the mercury is being pulled down by gravity. And when this column of mercury is 76 centimeters, 760 millimeters tall, the pressure of the atmosphere is equal to the force coming down from gravity, and so it just stays there. Now, mercury is toxic, and I listened to a really cool book called A Brief History of Almost Everything by Bill Bryson. I highly recommend it. He tells a lot of science-y stories, but in not horribly science-y terms. And so, it's actually pretty entertaining. Many of these early scientists were playing around with toxic substances, and they didn't know it, and so they ended up dying prematurely. So I'm sure Torricelli had fun playing with mercury, but he did not live a long, long life because of it. So he made this barometer, and then, who knows how people get ideas. He took it up a mountain. Like, here's this heavy thing of mercury. Let's take it up the mountain and see what happens. Well, you take it up the mountain, and the atmospheric pressure decreases, and the column of mercury gets shorter and shorter as you go up the mountain. Because the height of this column of mercury is related to the atmospheric pressure. If the pressure is less pushing down, then the column of mercury is going to be shorter. And then when he brought it back down the hill, the mercury column went back up again to where it had been. And so this barometer can be used to measure atmospheric pressure. And the atmospheric pressure does vary from day to day. It can actually vary somewhat from one corner of the room to the other if you're measuring it very, very carefully. Well, the average atmospheric pressure at sea level is 760 millimeters of mercury. And so they pretty much have defined that. They say, okay, at sea level, 760 millimeters of mercury exactly. That's what they decided. So 760 millimeters of mercury. It seems like a weird unit for pressure, but when we think about this barometer, a height of a column of mercury then makes sense as a unit of pressure. So a millimeter of mercury. When the weatherman talks about atmospheric pressure, he's using inches of mercury because we're Americans and we're stuck on not using the metric system, right? So he's talking about, well, it's 30.92. And he doesn't give the unit, but it's inches of mercury. It's an odd unit, and so they made a new unit. It's exactly the same size. It's a torr, and that's named after Torricelli. So 1 torr is exactly the same as 1 millimeter of mercury. So you'll hear both of them. 760 torr, 760 millimeters of mercury. They're both the same. Any questions about a barometer? So these are units of pressure. Pressure is something that can be measured. It can be measured in inches of mercury. Atmosphere is another unit. We use this a lot in chemistry. 1 atmosphere. That is the pressure of the atmosphere at sea level. It's 1 atmosphere.
What's a bar?
Pardon me?
What's 1 bar?
What is 1 bar? That's a good question. It's not on this table. I don't know off the top of my head, but it is a unit of pressure, and there can be millibars as well. Pascal is a unit that physicists use a lot. It's a Newton per meter squared. Pressure is a force per unit area. Newton is a unit of force. Square meter is a unit of area. So we don't use that one very much. You're probably familiar with PSI if you've ever had to inflate your car tires. You know, so many PSI. That's pounds per square inch. Pound is a unit of force per square inch. Then we have torr, which is the same as a millimeter of mercury, and inches of mercury, and atmosphere. The way these pressure unit tables are set up, 1 atmosphere is equal to 29.92 inches of mercury, which is equal to 760 torr, or 760 millimeters of mercury. That one is exact. 760 is exact. So it does not have 2 significant figures. It's exact. 14.7 psi, or 101,325 pascals. So the pressure units, the ones you should know, let me write this down for you. 1 atmosphere equals 760 torr. You should memorize that one. We're going to use it a lot. You'll probably memorize it whether you want to or not. Which equals 760 millimeters of mercury. If you needed inches of mercury and you didn't remember the 29.92, you could calculate it by just converting millimeters to inches. It literally is a measure of distance. So then, of course, we need to be able to do conversions with pressure units. So this is another way that these units are sometimes stated. 1 atmosphere equals this and this, 1 atmosphere equals this, this, and this. And so all of these are equal to each other. And what's nice about this is you only have to do one step for unit conversions with pressures. You just pick the one you want and divide by the one you have, and you're done. So let's do an example. Convert 35 psi to torr. So we've got 35 psi. We're going to multiply by the unit we want and divide by the unit that we want to go away, right? So it cancels out. You go to the table and 760 torr. Okay, so 760 torr. And then in front of psi is 14.7. No multiple conversions or anything. Can't find my calculator. 35 times 760 divided by 14.7. How many significant figures should that have? I heard mumbling. 2. 35 only has 2. So my calculator's telling me 1809 plus stuff. What should I call that? The best thing to do is to call it 1.8 times 10 to the 3 torr. Because we want to avoid ambiguous zeros. Okay? Let's do this other one. 30.41 inches of mercury. And we want to convert that to atmospheres. So we multiply by atmospheres, we divide by inches of mercury. We look in the table, 1 atmosphere is 29.92 inches of mercury. Units work out. 30.41 divided by 29.92. 1 point, how many sig figs should we have? 4. 1.016 ATM. That's atmospheres, not an automatic tiller machine. There's no money involved. Any questions? The manometer looks like manometer. It's a manometer. Barometer measures atmospheric pressure. Manometer is used to measure pressure in a container. So here we've got a container of some sort that has a gas in it, and we have a U-shaped tube that has mercury in it. Now, if both sides of the tube were open to the atmosphere, what would the mercury do? It would even out. It would just go to the lowest point that it could, and the height of mercury in each side, each arm, would be the same. But this side is not open to the atmosphere. There is a gas in this sealed container, and it is exerting a pressure on the mercury, and it's pushing down. And it's causing this side to come up. And the difference in pressure between outside, which is atmospheric pressure, and this gas is the difference in the heights of the columns of mercury. So you actually just use a ruler and you measure the differences in the heights, and that's the difference in pressure. You have to know the atmospheric pressure. And then you just add on the side. What is just really cool to me is a lot of these gas experiments, most of them were done a very, very long time ago. And, they had no technology. And yet they were able to figure out some really, really cool stuff. They didn't have electricity. They didn't know about electricity yet. But they were able to do experiments with gases and measure pressures and do all this really neat stuff.